Hello everyone, Monica the Tutor here, and today we're going to be going over how to find limits algebraically, just like I said I would last video. So it's kind of the same principle. It's still a limit. Like it's still you're figuring out what your y value is as you approach some x value, as you get very close. So essentially, basically, you are kind of solving for what the value is at that x value. So what the y value is at that x value. So kind of example will be, let's say we have the function x squared. Oh, let's say we have 3x minus 4 squared minus 2. That's f of x. So now let's say the limit, we want to find the limit as x is approaching, let's say 3 of f of x. We are essentially just going to plug in this value of 3 into our equation where x is. So it'll be 3 times 3 minus 4 squared minus 2, which is equal to 3 times negative 1 squared minus 2, which is equal to 3 minus 2, or 1. So the limit as of f of x as x approaches 3 is equal to 1. And that's your answer. So it's kind of pretty straightforward and simple. Like you're essentially just doing the same thing you would do to find the y value of of a line. You would just plug in your x value and see what y value you get. But remember, let's say we were to graph this real quick. I'm not gonna graph it with perfect accuracy. But the vertex is at 4, -2. It's going somewhat like this, right? So as x approaches 3, I understand this x approaching 3 looks nothing like this R1. But remember, it's not actually at 1, it's just very close to 1. Because this is also, it's not like x is at 3. X is getting very close to 3, infinitely close to 3. And so basically your y is getting infinitely close to 1, which is kind of how the limits work, essentially. So let me give you guys another example real quick. Let's say, let's say, let's say we have the line uh 2x minus 3, so f of x is equal to 2x minus 3, uh 4x plus 5. And let's say we wanted to find the limit as of the limit of f of x as x is approaching, let's say, 1. Okay, we would plug 1 into wherever there's x. So 2, 1 minus 3 over 4, 1 plus 5. This is going to be equal to 2 minus 3 over 4 plus 5. Or in other words, just negative 1/9. So we were to graph this and this line, and we were to kind of see, oh, at 1, where is our value? Where is our y value? It would be very close to negative 1/9. And here, let me just graph that on Desmos for you guys real quick and kind of show you. Let's say 2x. So let me pull this over. If we look at what x is at 1, this is 1/9, which means that as we're approaching it from the left and from the right, we are getting very close. Let me get to actual 1. We are going to get. I'm trying to get there, but you saw it at the beginning. At 1, it's right here. Okay, it's right here. This is negative 1/9. So as we approach 1, we are going to get very much close to negative 1/9. Okay. So now I need to introduce one more rule too. Um, This will normally come when you are working with these kinds of equations, rational equations. And that is if you are finding the limit of something that makes the denominator zero or makes essentially makes the whole fraction undefined, you cannot you have to do some work to your equation to make it not that. Your limit when you are defining algebraically should always be defined. I don't know why that's the case. It's just the case. Like, I know with graphically you can have an undefined limit. Algebraically you won't, and that's usually what I can explain. It's just when you graphically when you don't have when the limits are undefined, it's because your graph it's a piecewise function. Usually because you have one segment going like this way, and then another segment going like this, maybe one like that. These are three separate equations. Equation one, oops, I don't know what that was. These are three separate equations. One, two, three that you've essentially mashed together onto one graph, and you are finding the collective limit. So if we were to find the limit of this point right here, let's say this is 1, it wouldn't exist because that's where two equations are intersecting. With our rational functions, let me go back to, let me just write this equation out. With rational functions, you're only working with one equation, which is why it should never be undefined particularly. Even if you are going towards an asymptote, usually it will not be undefined. So let's say f of x is something simple. Let's say it's x squared minus 1 over x plus 1, and you want the limit of this as x is approaching negative 1. Well, yeah, so let's go about it as we normally would. Let's plug this. So negative 1 squared minus 1 over negative 1 plus 1. This is going to be 1 minus 1 or 0 over negative 1 plus 1 or 0, which will make this whole thing undefined, which cannot be. When you solve for limits algebraically, you cannot get an undefined limit. It has to be a number. So you have to do some work to this. And maybe take a second try to think what it could be, or come back and I'll explain it real quickly. Okay, hopefully you thought about it. And what's going to happen is we're actually going to factor here. So we're going to break the top up is a perfect square. So we're going to break it up into x plus 1, x minus 1 over x plus 1. So now, when we cancel these two out, we're left with this. And this is basically our new f of x that we're working with. So when we find the limit as x is approaching negative 1, we are actually working with x minus 1. So when we plug negative 1 into this, we're going to get negative 2. And that is our answer. If that makes sense to you, that's great. If it doesn't, don't worry. We got plenty of practice coming up to work with it, but hopefully this is kind of making some understanding. And so factoring, what you normally do, you will need to work with the equations. So there'll be factoring, rationalizing, all kinds of things. But let's go to some of these preset examples I have here. Give them a try. See what you can do. Maybe you'll get them, maybe you won't. But that's okay. I'll just pause the video, come back once you've given them a try. Okay, so hopefully you gave them a try, and maybe you got them, maybe you didn't. But no worries. Here I am to explain. So let's go here with this top one. What can we do to kind of work with this? Because if we plug in 1 to this, the the first red flag you see is when you plug in 1, cube it, and plug in 1, square it, you're just going to get 0. So that's how you know that you cannot just plug 1 in here. You have to do something to your equation. You should always try substituting first when you're solving for limits. Always try plugging the limit value they want into your equation, and because that's the easiest way. If that doesn't work, then you have to start like factoring. But let's get to factoring. What I see is everything here has an x in it every term. So let me pull out the x squared, which is the least one. So x squared from both ends, x squared plus 2x minus 3, x squared, x minus 1. So let's take this a step farther. First, we can just cancel these out. Let's take what we have so far a step farther, because you plug 1 in here, you will still get 0 in the denominator, which we can't have. So now let's try this. Let's break the top even more now. So if you see, this is actually x plus 3, x minus 1, and now it's going to be all over x minus 1. So this will cancel, and now we are essentially finding the limit of, as x approaches 1, of x plus 3, which is just 4. And that's our answer. So take a quick look at the process. This is kind of what you do, and that's how you get to your answer. Okay, so now let's try the next one. How am I going to do this? Because I plug 5 in here, I'm going to get 25 minus 30 plus 5, which is still 0. So I cannot do that. So we need to simplify. Well, I know the denominator can be factored, and the numerator I see as a common factor of a common multiple of 12. So now what I can do is I can just do 12 x minus 5 all over. This is x minus 5, x minus 1. Just cancel, cancel. Now we're essentially finding the limit as x approaches 5 of 12 over x minus 1, which is 12 over 4. So now our limit is 3. So that's how we did that one. Take a quick look at it. Hopefully you understand. Okay. Alright. Now for this next one, there are actually 2 ways to do each one of them. I'll show you both ways with this one right here. I'll show you both ways with this third option, like with this one, and then for the fourth one, do whichever one you like. But let's get started. So let's say limit as x is approaching 9 of x minus 9 over root x minus 3. Well, let's see. Let's plug 9 in first. Let's see what happens. We plug in 9 to the bottom. We have root 9 minus 3. What does that equal? So that's root 9 is 3, minus 3 is 0, which means we cannot do direct substitution. We have to simplify. So let's think about this. There are 2 ways. You see the square root, maybe your first thought is rationalize, which is one of the ways to do it. You rationalize. Another way is actually, this in itself is also a perfect square. This is actually root x minus 3 and root x plus 3. Think about it for a second. Root x times root x is x, and then negative 3 root x and positive 3 root x will cancel, and then negative 3 times positive 3 is also negative 9. So it does work. And then we can just cancel this, and we'll have now the limit as x approaches 9 of root x plus 3, which will be 3 plus 3, which is 6. So that is one way to do it. Let me show you a second way underneath here, and that's with rationalizing. So I would do x minus 9. I'm not going to write the limit part. Root x minus 3. We multiply everything by conjugate. So root x plus 3. Root x plus 3. I'm not gonna multiply the top out. I'm just gonna multiply the bottom out. So that'll be x minus 9. Root x plus 3 all over x minus 9, which coincidentally is this. So that cancels, and now if we plug in 9 again to the numerator now, which is the only thing we have left, we're going to get 6 again. So that's how you know you got the right answer, and that is the 2 different ways. Usually you basically only have to rationalize or factor, or a combination of both. But, I didn't mean to erase the whole thing, I'm sorry. X minus 3. Okay, let's go to the bottom. This one can also be factored. You can rationalize this. I wouldn't recommend it. I think factoring is easier. Factoring is always easier. This bottom is a perfect square again. So we can do root x minus 4 over root x plus 4 and root x minus 4. And I am so sorry. One thing you should have, the first thing I should have done is see, does 16 work? No, it doesn't. You plug in 16 initially, you will get 0 in the denominator, which means you will get an undefined limit, which cannot happen. So, this will cancel, this will cancel. We're going to be left with 1 over root x plus 4, which essentially is just 1 over 4 plus 4 or 1 over 8, which is where this is all coming from. So hopefully that kind of helped you guys out understand finding limits algebraically. The next video I'll go over is continuity and how to tell if a function is continuous or not. But yeah, I hope this helped you guys, and as always, let me know in the comments what you guys want next from me. Peace.